Another method to draw Lewis structures is you can actually, for the octet rule only, this won't work if you're not using the octet rule, you can actually figure out how many bonds you need just by doing a little math. It's kind of a little logic puzzle. This does not work for the octet rule for boron and beryllium. Beryllium only needs 4 electrons. Boron only needs 6. And if we break the octet rule, these we're just going to make single bonds and use the electron pool method, make sure we have all the electrons accounted for. But if we are obeying the octet rule without pushing electrons around, we can figure out how many bonds are in a structure. If we looked at, again, familiar CO2, we know that we have 16 electrons available. And because there are 3 atoms, and each one needs an octet, 8, 16, 24, we know that it takes 24 electrons to satisfy that. By looking at this, we say, okay, we are missing 8 electrons, and that means since electrons are going to be shared, this means we need 4 bonds to make up for what we're deficient. So just by looking at those 4 bonds, we can get a carbon dioxide structure that looks like this, and then we fill the octets with the remaining electrons to make sure that all 16 are there. If we looked at carbon monoxide with 10 electrons, and then there's 2 atoms, so 8 times 2 is 16, we can see here we are short 6 electrons. Since electrons need to come in pairs, we can make up for that by sharing 6 in 3 bonds. And you can see how carbon dioxide gets 3 bonds. There's 6 electrons, we need 10. So 2 and 2, octet, octet, those are both full. The last example is the carbon dioxide example, carbonate example. And we can see we have 6, 12, 18, 20, 24 electrons, because we have to count those extra 2 again. There are 4 atoms that each need an octet, so 4 times 8 gives us 32 electrons. That shows us that we are missing 8 electrons in order to satisfy all the octets. We can make up for that by sharing 8 electrons in 4 bonds. That means we can share them to kind of make up for that and fill the octets. There are 3 atoms here with the oxygens. So one of them is going to get a double bond because we need 4 bonds. It doesn't matter which one. We would need to draw resonance structures for this. But there is our 4th bond. We make sure all 24 electrons are accounted for and all 4 atoms have a full octet. So again, this only works when you have an octet rule being filled. If we were to try to do this with another molecule, XeCl4 was an example we did in the other video. We can see here we have 36 electrons, but we would only need 40 to fill the octets. Well, that means we only have 2 bonds that we would need to share. And you can see we can't bond 5 atoms with 2 bonds. So this has its limits. We just want to use the electron pool method and give single bonds to everything. Fill all the octets like we normally would. 8, 16, 24, 32, and we still have extra atoms, so they're going to go on the center. Using this, though, we don't have to push the electrons around like we would in the other method, but pushing them around is still a very useful tool to use to figure out how we can balance structures and draw Lewis structures, which is a skill you'll use more and more as you go on in chemistry. But this is the one that's in your notes, so I wanted to show it to you. The electron pool method is, if you can understand it and you are good at it, it works all the time. It's definitely a little bit more versatile. This gives you a little bit of a reassurance for how many bonds you need to account for when you're drawing your structure. But it only works if you have for the octet rule. Okay, that is your second method for Lewis structures, and that's the one in the notes, so I just wanted to show you a quick summary on the board. There's another summary video for the electron pool method, which is probably a little bit more useful.